Welcome. My name is Philip Lovejoy, and I'm the Executive Director of the Harvard Alumni Association. It's my pleasure to welcome you here this afternoon on the East Coast. A few housekeeping notes before we begin. Please note that today's program is an off-the-record opportunity created for our reunioning Harvard alumni, and we're using Zoom webinar, so your camera and audio will remain muted. Closed captioning is available by selecting the CC button at the bottom of your screen. And if you have a question for today's speaker, please send it in the Q&A box below. It would be great for you also to include your class year with your question. Today we have hundreds of Harvard College alumni with us who are celebrating their 5th to 75th reunions. We also have members of the Crimson Society, representing those classes who have already celebrated their 50th reunion. While I miss being together on campus, I'm delighted that we have alumni from around the world, and I am here in New Hampshire. Thank you all for joining us. I'm delighted to briefly introduce today's speaker. Dr. Vijay Janapa Reddi is the associate professor in the John A. Paulson School of Engineering and Applied Sciences and director of the Edge Computing Lab, also at SEAS. The Edge Computing Lab is a cross-layer and interdisciplinary research group that focuses on solving problems at the intersection of different fields. Professor Janapa Reddi is also a founding member of ML Commons, a nonprofit organization focused on accelerating AI innovation. Personally, I was delighted to hear about Vijay's passion for STEM education. He is responsible for the Austin Independent School District's hands-on computer science program, which teaches programming and much more to middle school students. I encourage you to learn more about Professor Janapa Reddi's background and many accomplishments through the link provided in the chat. We're fortunate to have such a thoughtful, dynamic researcher, teacher, and thinker with us today. I'm thankful for his time and commitment to our alumni community. Without further ado, I'm delighted to welcome Vijay to the virtual stage. Thank you.
Awesome. Thank you, Philip. Good morning, good afternoon, good evening, wherever you are. I'm super excited to be out here because I'm about to talk to you about something that's actually quite passionate about. And one of the things that I'm hoping that will come out of today's talk, just kind of looking at this presentation, would be that you're inspired that there is something that you and I can actually work on that is much bigger than what kind of boggles our mind on a day-to-day basis. And so that's going to be all about 1,000 words in 1,000 languages, democratizing speech technology for the masses. So let's dive in. How many of you have ever done this? Where you say, okay, Google, and then a machine wakes up and it responds back to you, and you go on having a conversation with it in some capacity. Maybe you don't say, okay, Google. Perhaps your favorite device happens to be one of the Apple series, where you say, hey, Siri, and the machine wakes up and it does something. All right, fine. Maybe you're not an Apple fan, but you're an Amazon fan. Either way, what you're effectively doing down here is really communicating with the device, right? You're using your own speech, conversational aspects of AI that trigger this machine to wake up, be able to understand what you're doing, and then actually respond back to some sort of task that you're asking it to do. In the examples that I just showed you, it's what we call as keyword spotting. Now, this is not general speech recognition. There's a very good reason I'm drawing this distinction. The key goal here is that you want to be able to empower a machine, a very small machine, specifically a tiny machine, something that's able to run with ultra low power efficiency, meaning something like a coin cell battery, something that you don't plug into the wall, something that kind of runs continuously at all times. It's not just when you're actually talking to the machine, rather it's always listening in a way that you can actually interact with it very much in a seamless sort of fashion, the way you interact with any individual person. And it's all doing this intelligent analysis on device, meaning it's happening right there where the data is or where your sounds are, and it's applying state-of-the-art machine learning techniques. Later on, once I start talking about machine learning in greater detail, I will explain a little bit about some of the nuggets around here. Today's talk is not going to be teaching you what machine learning is about at a very low level. What I want to focus on today is really to kind of get you excited about the possibilities of knowing how to use this black box tool that the entire world is excited about. And I'm going to talk about this specifically in this context of keyword spotting, where the keyword, be it Alexa, Siri, hey Google, whatever those keywords are. How do you get the machine to kind of wake up? And what are the implications when you think about that at a one level deeper? And that's where I'm going to take you. And again, this is very different from what we call a general automatic speech recognition, where you're able to have full-on conversations with the machine, because that is much more power hungry and they're also much larger. And in other words, this is not something that's going to be running right in front of you. It's probably something where your voice is being sent over to the cloud, and it's somewhere in Google's data centers or Microsoft's data centers where all this data is going to get processed. So the key focus is really about sort of like this critical bits and pieces of information that we kind of take for granted when we're talking. It's being able to identify critical words in there so you can kind of build a bigger picture. And that's what keyword spotting is as a definition. And I'm going to be using that quite a bit later on. Now, keyword spotting is just one part of a much complex pipeline in the world that we live in. We're going to be talking about what's going on here, but typically, for example, in those cases where I showed you where you have a smartphone in front of you and you say, okay, Google, and the machine wakes up. And then you go on talking to it. A bunch of things happen. This is what we call a speech to text. You're taking your speech, the machine translates that literally into text. And then it uses NLP, natural language processing, to understand what you're saying. And then performs a certain skill, a task that's running somewhere out in the cloud. Like maybe you might say, hey, Amazon, hey, Alexa, play my favorite music. It's one of my favorite things to say in the evening. So then, well, it goes, understands what I'm saying in terms of playing my music, looks up the history, generates a response, and then it does text to speech, where it generates a textual response, but that needs to be generated into a vocal photosynthesis that then comes out of the speaker. Now, speech is remarkably powerful. It's key because it ties us, it creates communities across the planet. Now, I'm not talking about speech in the context of a machine. I'm talking about speech in the way that you and I are able to understand each other right now. And from that sort of a perspective, how important is it going to be about making this sort of speech capability working in conjunction with these machines, like these complex pictures that I'm showing you here? How amazing would it be if we could actually enable speech in many different languages? And that's kind of what the crux and nugget of today's thing. If you can do that, there are lots of interesting applications and capabilities that we can unlock. For example, you might already have come across this example where the device in a way is constantly listening, where it, based on some music it's actually listening to in the background, might just be something that's coming out of some of the speaker. Your phone actually knows what that music is. I mean, that's pretty remarkable, right? Now, these are the kind of things that are actually happening today. They're pretty cutting edge, but there's so much more we can do. Imagine, for instance, in the future, you're able to talk to your car. You get in, instead of pushing a button down to roll your window down or start the car, you just say, start the ignition or lower my window. These bits and capabilities, imagine if everything was like that, where you could literally just have seamless integration. Today, when we are interacting with these machines, we are interacting with a hunk of metal at the end of the day, because you are learning how to interface yourself with this machine. Instead, what I'm talking about is having seamless integration as if you're working with another human being, or you're just communicating and the machine is actually understanding what you're saying and performing the necessary mechanical actions. Well, that's some of the possibility that's coming down in the future. Now think about it, just take for a moment and think about all the devices that you have around you right now. And think about what your world will look like if every one of those devices right around you right now is actually intelligent and it's actually able to understand what you're saying and is actually able to respond in a way that actuates some sort of system. Right? Now, that's the kind of world that we're actually going to be heading into. And it's coming really fast and it's really hard. But that's just the tip of the iceberg. I'll walk you through today what are some of the big problems around this space, even though it's remarkably exciting. And a lot of us researchers are all excited about it. And if we can enable intelligence in a device, in consumer devices, where it's conversational speech that the machine's able to understand, you can unlock a whole new range of consumer applications and capabilities. Simple thing, for instance, I wake up every morning and the first thing I do is walk straight to the coffee machine and I turn it on. Now imagine if that's like, a seamless thing would be, I just walk by and I just say, make my coffee, or I'll put the bread in the toaster and I just say, toast for 2 minutes, add something, right? So that would really change the way we interact with a lot of these machines. Now, that's just one example. That's just a speech example, which is what I want to focus on today. But another area that's actually really interesting is sort of like, imagine if we could put that sort of intelligence capability into all these embedded small little devices around us. Then the world could be a much better place, because you could have remarkable real-time analytics for health, for vision, for the impaired, there are many different applications that we can actually unlock. And that's really what's exciting about this, right? So now, one of the key questions that I just want to focus you on, out of all of the grand possibilities, is imagine where every device effectively has a voice assistant inside it in your favorite language. This is important. Question for you, and I'd love it if folks will like just chime in Q&A and chat. The question that I have for you is like, when was the last time you interacted with one of these state-of-the-art devices in your own native language? My mother tongue is actually Telugu. It's an Indian version. And rarely, I've never been able to interact with any machine around me in any language outside of English, be it my laptop, be it those tiny little endpoint devices like Amazon, Alexa, and so forth. The problem is, when we look at the world and we look at the technology, it's a very small sliver of people that are benefiting from all of this. And there's a really good problem that needs to get solved. And that's what I'm going to be taking you all through as a journey today. So if you look at the whole world, and you look at all the different people that are on our planet, well, there are many different languages that are spoken. In fact, there are over 7,700 plus different languages on this planet. And we're all human. At the end of the day, it's just different language. Machines, all this technology should be globally accessible, should be widely accessible to everyone. But if you look at what's going on, we only support a very small subset of conversational AI capabilities because of data. It really comes down to data. Now, this is going to be the one slide where I'll get a little geeky and try and help you understand some of the core nuggets in order to be able to build much more deeply into some of the core problems that we have to solve in order to enable speech technologies globally at a massive scale. So from any machine learning or artificial intelligence pipeline, this is a traditional workflow that you walk them through. You start with collecting data. Without data, in other words, if you don't have data that says, hey, this is a cat and that's a dog, there's no way you can train an algorithm to automatically know whether it's a cat or a dog. So data is extremely key in machine learning systems. You collect a whole bunch of data. We'll be talking a lot about data today, so I'm not going to go too deep now. We do a little bit of pre-processing, clean up the data a little bit, and then we get into training a machine learning model. A machine learning model is effectively, you can think of it as something that's a pattern recognizer. That's really what it is. It's a bunch of these small little neurons, very much how our brain is wired together, that are connected up in some interesting architectures. And it's taught very much the way, I teach my kids, they make a mistake, I tell them don't do it. Make a mistake again, I tell them don't do it. You reinforce the good habits, and effectively certain neurons get stronger for certain keywords effectively. So there's a training process that's involved, and it's a very iterative process. You train this piece of algorithm, this pattern matching algorithm, and then you evaluate it. And you will see how well it works. So given some sort of data, and this is key, given some sort of input data, let's say, for example, I want to know the numbers 0 through 9. I want the machine to be able to recognize these digits. If I say 0, I want it to light up and say it's a 0. Well, that's my training data set. Now that data set is obviously put into this neural network, and it's taught repeatedly with a lot of different samples. So I might have to collect 1,000 of the zeros, 1,000 of me saying ones, 1,000 of me saying twos, and so forth. And you feed this into the neural network model, and then you go into the evaluation stage where you evaluate how well does the network really work. And if it works well, in other words, if it's able to get predictions around 95% or something like that, then you would go on to the final stage of actually deploying this on device, which is very much what's inside your phone or inside your Alexa and so forth. Now, the crucial part of this entire thing is really this, the front end part. So I'm going to focus very much today on this, because this is where the future is really going to lie. If we want to enable these kinds of technologies at global scale, This is really the problem that we have to fix. Of course, you still, even if you get all the data that we need, there's a second part, which is actually how do I accelerate that whole pipe? In other words, how long does it take? Today, a lot of these mechanisms that exist in order to go from having the data to actually being able to deploy the model on a tiny little device is tied up in many of the big tech firms. And so if we want to enable global access to this technology, we have to engineer new systems, do the research and engineer new machine learning pipelines that are able to shrink that thing so that you don't need to, have just massive amount of capital in order to build this technology. And that's kind of like the real essence of being able to build 1,000 words with 1,000 languages. In other words, we want a machine to be able to recognize 1,000 words in any language. And how do we get there? Well, the fundamental problem is this, right? We want speech commands, keyword spotting and speech commands for a whole planet. And what this is kind of telling you, the size of each of these individual circles is really about the population count. There's so many speakers in Mandarin, English, Spanish, and so forth. But if you look at that long number of people that are there, there's a very long tail, as we call it. In terms of data, now remember I told you data is king for being able to build these intelligent machine learning methods like voice assistants. Now, when you need lots of data, lots and lots and lots of data to be able to train these things. Well, okay, if it's English or if it's Mandarin, there are large data sets. Yeah, but as you start looking at the world's population, and given the fact that the population speaks so many different languages, the data diminishes really, really fast, which means there's going to be many, many people out there who simply do not have access to this rich technology that we take for granted. And so how do we sort of go about solving this problem? Because there's a lot of technological advancements that are needed. In effect, what we have to do is we have to build data sets similar to the way we have done for English. For example, a good reason that Google, Amazon, all of these large big tech firms are able to do this for us is because in English, there's a lot of spoken speech. There are these big data sets that they can crunch through, where they are able to say, they have the ground truth, where if I say 1, they know it's 1. Then you train the machine learning model. If it says it's a 0, then you say, nope, you're wrong. So you back propagate and you correct it. And until it figures out that, oh, this sound corresponds to a 1. So it'll say that it's a 1. So then it knows how to take speech and convert it into text, which is the first thing that I showed you in that figure of how things are tied together. So we need to create these data sets. Now, okay, well, the question is, how do we create all these different data sets that are just as big so that everybody can benefit from just the level of access, for example, we have in English? And that leads to this fundamental question about democratizing machine learning, which is an extremely important thing that we have to enable. Might be a little bit of a philosophical ride here, but I just want to say that one of the key things that I think is, if we're not careful about this machine learning and AI technology that's actually being deployed out in the field, this could literally start creating a new social divide in the ecosystem, because this technology has to be something that is accessible to everybody. And so we need to start working on identifying technological solutions for this. So at this point, hopefully you understand that data is extremely important. So I'm going to talk about what's data engineering, what goes on behind building the data set, because I want you to have a hands-on grip on that, because then you will have an appreciation for what I'll come about later, where we start to automate this entire process to help get to 1,000 words in 1,000 languages. The first thing is identifying the requirements. Requirements are like, what are the words that you want all these consumer devices around you to be able to recognize? Then you've got to collect that data. So somehow you've got to figure out how you're going to use it. One of the big problems in machine learning is really getting the right permissions and access rights. For example, in Baidu, built this massive data set, which was really remarkable, and they wanted to make it accessible for everybody. But they botched up one thing, where the lawyers caught them and said, you did not phrase this one sentence correctly. And they said, this means that you cannot release the data set, which is a very large data set, which would have had a huge impact. But if you don't get the rights right, then you can't use it. So you have to identify the requirements very carefully. And I had to think about what these requirements are going to be for every particular thing. Now think about it, like you are not building a consumer product that spreads across the entire kitchen. Maybe Samsung and a few others have a whole bunch of different things, but everybody's got their own custom thing that they're really interested in building, right? So everybody's doing requirements. Keep that in mind. Second thing is then every organization then has to go in and start gathering the data. In other words, collecting the sounds that are needed so that they can train that machine learning model. This means you've got to identify the people who are actually involved. Well, if you want a very sophisticated voice assistant that actually works across a diverse population, that is not just going to work for English accents. So for instance, even some of the latest voice machines don't respond well to me because I tend to have a little bit of an Indian accent in there, which still, is remaining from my long past days when I was in India. But when I give that same exact machine over to my mom, oh, it's a complete zilch, zero. It does not work. It does not recognize her strong Indian accent. So the point is that that's because they didn't have the right data that's actually demographically sort of, capturing the biases that are there. So you got to get the right people in the room in order to get those initial recordings. Then, of course, there's a process of actually how do you collect? You've got to collect the data so that you're taking into account background noises and all those kinds of things. Then you've got to actually do the right labeling. Someone gives you a sound. Now, the sound you don't really know until you hear it. Is that a yes? Is that a no? Is that a zero? And so someone's got to do that labeling because that's needed. Then you've got to have a wide variety of different data sources you're syncing it from. Then, of course, after you've collected this mass amount of data, then you've actually got to make sure that the data is clean. In other words, you've got to make sure that no one is maliciously saying no when instead they were supposed to say yes, and vice versa. So you've got to validate that. All of this, you can start imagining, is starting to add up in terms of the cost and the time complexity that's actually involved in here. Even if you built all of these things, after you've gone through requirements gathering and refinement, and you've got this data set, which you can then train a model with, you've got to continue to improve it because over time, your consumer base is going to change. You got different people who have different needs. So maybe initially your market is just the US, but maybe later it ends up being Asia. So you have to continuously start improving your data sets. Now, I'm talking about this because all of this means that data engineering is something that every institute that wants to apply any AI is going to have to do this. And this is costly, tedious, and error prone. So how can we sort of do things a bit differently, for instance? The way much of the AI field has kind of moved about is because there are large data sets. And I want to give you an idea of just how big this data set is going to be, because so far you know the mechanics, but you haven't quite realized how big it's got to be. So for example, ImageNet allows us to tell whether it's a, if you train a machine learning model on ImageNet, it allows you to know whether it's a cat or a dog or a bus or a plane and so forth. Because someone, actually Fei Li, who was a professor at Princeton, is now at Stanford, actually helped build this ImageNet, which is what really gave birth to our artificial intelligence at the scale at which we're using today. And this happened actually around 2007 when she actually created this massive data set with her students. Now, that's just for being able to classify. Classify means being able to say whether it's a cat or a dog, that's a picture. Now, then you got to get into starting to detect things. So let's say you're building a shopping application, right? And you want to identify what's the piece of clothing that an individual is wearing, because then maybe you want to buy that exact same thing. Or for instance, you're building an autonomous car and you want to be able to identify where exactly is a motorcycle, for instance, right? Or where is there some animal or something that's coming up, so you got to do detection. Now, these seem like they're just images. Well, I just gave you one example of classifying, but that's very different from detecting. So Microsoft had to build a data set with over 2.5 million images. And these are actually quite old at this point, but they're like textbook style examples. Then if you're building something like autonomous driving, there are these massive data sets where you have to physically drive the car, and then you have to do what's called segmentation. As you can see, the colors in this picture are different because that allows an autonomous car to actually know how to navigate this space. What's the road? What's not the road? Who's a person? And so forth. Right? So you need to have a massive amount of data set. Don't be fooled by the fact that Waymo from Google only has 1,950 segments. These segments contain an insane amount of data coming from many different sensors for an autonomous car. Similarly, there are several other data sets at large, right? But by and large, the key point that I'm trying to focus on is many of these are manually constructed, literally manually constructed, meaning you either hire some set of people and you pay them. And if we are trying to deploy this sort of technology, right, machine learning technology globally, then not every company is going to have the kind of access and scale that Google, Microsoft, Baidu, or Alibaba, like these major tech firms have. So the question becomes, how do we start democratizing this kind of technology? I've given you examples of image and speech and so forth. We are particularly interested in the speech side. So the key takeaway really is that building these data sets is extremely costly and tedious. Now, the key thing is that we need to have public data sets out in the wild. These public data sets are extremely important because public data sets can actually help drive innovation. Public versus private means, for example, we looked at Microsoft, we looked at Facebook and Google, and we looked at their research publications that are coming out in the best of conferences. And public means these are open data sets that were created by academics such as myself and other people. And non-public data sets means data sets that these companies actually built on their own, and they're using their technologies on that data set. Because again, remember, data set is a rocket fuel for AI and machine learning. And you see that across a wide number of papers that we analyzed from the last 3 years, the vast majority of research is being done using publicly accessible open data sets that are fundamental building blocks, right? And so the question is, how can we start creating more data sets? This chart is simply doing a breakdown between Facebook, Google, and Microsoft. And the point is that across all these major organizations, even though they have their own internal private data sets, they still rely quite a bit on actually using open data sets in order to fuel their research. Now, data is just one of the key things, right? So if we want to build something like 1,000 words or 1,000 languages, are we seriously going to go through that whole costly data engineering process for every single data set? And just imagine the process that's involved if we had to get for every single word. If I say yes, no, maybe if I want to have this in Spanish, in English, there's going to be someone who's going to have to record that sound. And not only that, they have to record that hundreds of times because you need to capture subtle variations in the way you say, yes, yes. Well, those are two, you hear them as the same word, but your brain has figured out how to amortize those differences to be able to say that, oh, that's roughly the same. That's actually the same word, yes. We've got to teach these machine learning models to do the same. That means they need to hear that there's many different sounds for the exact same thing. So it's a very, very costly and tedious process. And if we don't start thinking about technologies that can automate this sort of a process, then, well, as I said earlier, a lot of this is going to start creating a massive divide in who actually has access to this technology and who does not. So what's another way of kind of, doing things cheaply? I already talked about why cost is a prohibitive issue, because we're not going to be able to get to that long tail that I showed you of having lots of different people. We're not going to be able to get to all of them, because are you going to pay for that data set? Why would you want to pay for a data set that might not directly benefit you, right? I mean, I wouldn't, because I don't know when that's going to cost, and data sets are extremely costly. So it's not like we're going to get sponsors. We're just going to start sponsoring data sets. So the approach that I talked to you about, which is sort of state of the art, doesn't really work. Well, our alternative approach would be community, getting you and me to contribute for free rather than building the data set. So let me talk about that a little bit. I'll give you a specific example of Common Voice. I wanted to ground some of these things. I encourage you to go and check out this link, Common Voice, which is effectively an open data set collection. I'll talk about this more. So Common Voice is a crowdsourcing platform which relies on people like you and me to actually go to the website and actually donate our voice. So for example, this is a screenshot that I took where, let's say you're going to speak into it, you're going to speak into your browser, they give you a sentence, and then you will record it. And then once it finishes, it'll move on, the next one comes in, and then you will give it a couple of samples. So this way they're using the community to actually build the data set, which is really remarkable and powerful, right? Similarly, but at the same time, now this is somewhat on the left-hand side of that data engineering pipeline I showed you. But then someone's actually got to listen and say, yes, this person, he or she actually recorded the right thing. Because you don't want the machine learning model to start thinking a yes means a no and a no means a yes. Because you can totally do that if you take the word yes, but then tell it, oh, this is actually no. If you tell it that, well, it doesn't know any good. It'll just think a yes means a no. So you can mess around with things. And this can lead into some serious production problems, right? So someone's actually got to listen to the sounds, play them, and then tell it whether it's a yes, they got it correct, or give it a thumbs down, saying like, nope, hey, someone's messing around with this one, so you got to throw this one out. There's lots of nuances involved in here. Now, think about the amount of manpower that's involved in order to get everybody to do this. Again, for 1,000 words in 1,000 languages, imagine if you can do this. That said, I want to be constructive. Common Voice is a platform that's kind of built on over 50,000 volunteers, chipping in and trying to help build this. As a result of creating a platform, keep that in mind. As a result of kind of creating a platform, what we're able to do is that there are 54 different languages in which there are data sets that people have actually contributed into, which is kind of beautiful, because getting data across so many different languages is remarkably hard. And again, remember, you've got to have a lot of data. And another thing that's really interesting, or for example, here you can see it's English. There's about 50 gigabytes. Really, to be honest with you, that's really not that big, despite the fact that there's a lot of data in here. And someone's actually gone and validated that data, right? Out of all of that total amount of recording time. There's a nice little license that actually allows you to reuse this data in order to train these machine learning models. Someone has to architect the data recordings carefully. There are over 60,000 people who have unique voices that have actually contributed to things. But pay attention to this one. Look at the stat there. 47% male, 14% of the data is female. The rest of it, if you're wondering, it's just, there's no metadata associated. The person recording it didn't want to share that. You should already be realizing what I'm getting to at this point. You don't have a balanced data set. What this effectively means is that it'll work well for male because there's a lot of that male data, lots of different pronunciations of words in there. But for female voices, there really isn't much. So what's going to happen? This machine is basically biased. By design, it's going to be biased. It's going to respond better to men than it's going to actually respond to women. So part of the problems of having an open ecosystem, right, is really that you can't control the way it's going to evolve. But at least there's some amount of good effort being done here, in that like they're reporting these stats, which is actually a huge step forward compared to where things have been in the past. Now, there are a lot of other tasks that need to happen. For instance, you have to, in order to do this public data engineering, relying on people, you have to prompt, you have to create an entire system in order to collect the data, saying yes, no, and all these different words. You've got to provide a mechanism to actually record these sounds on the web. Then you have to have attributes like the one I was talking about, for instance, the demographics. You've got to make sure you get a balanced set. You got to record that. You can't really control it. After all of that, you've got to validate this as to whether it's a yes or no. Is someone actually saying this? You simply recording it and building a model like that, that is the biggest mistake anyone can make, because there could be things in there that'll show up in your production pipeline where it might be totally biased. Like, for example, in the male versus female example I gave you. And then you've got to create the data splits, nuanced detail. But the point is that, all of this is, again, a tedious process. Even so, we went from talking about big corporations potentially building these data sets by themselves, right? Then I showed you that these big corporations are in fact actually using a lot of public data. They actually want to rely on public data because it enhances their credibility, because they're able to one can actually reproduce their results, which is extremely key in machine learning. Then I said, okay, well, even if we did all of that, it's costly and it's very tedious, but can we rely on the community? So that's the second option I'm giving you here, right? And I'm still telling you, it's still very tedious and costly. All of this, even after I've talked about all of this, this is just the front part. This is just the data. Then there's the rest of the entire pipe you actually have to accelerate in order to take that data and create value out of that data. You have to train a machine learning model. Then you've got to learn to evaluate this properly. Then you've got to actually physically deploy this and understand whether that deployment works well. This is a very costly and tedious pipeline today. As much as we think AI and machine learning is pervasive across many different technologies, and it's got a massive amount of growth potential, what I fear, though, and a lot of people fear, is that it's not really globally accessible piece of technology. And so increasingly, we need to start thinking about how to cut down the level of expertise that is needed in here. Machine learning engineers or AI engineers are paid an insane amount in order to leverage their skills because there's so few of them out on the planet. So we need to think about democratizing this sort of data engineering pipeline as we move forward. Let me give you an example of how we might be able to do this. I'll just give you one point example. This is something that we just did, it was state of the art. So let's take this back all the way to the beginning again. I like to tie things back. Let's take this back to when we were talking about, hey Siri, okay Google, right? Oh shoot, my machine.
Hi, I'm
sorry.
Siri. I think you've got the wrong assistant.
Sorry. Happens all the time, and I thought I disabled everything. So let's say we want a consumer device to respond to some word. And again, remember, look around you. There are many different consumer devices around you. They're not all made by the same organization or company. So every company might want their own set of keywords. For instance, I don't want a toaster to know how to bake. I want a toaster to respond to toast. I want an oven to respond to bake, not start or stop or just some arbitrary thing. So everybody has their own set of critical keywords that they want to do. I imagine you could just write this, just the way you type an email. Just imagine you just kind of write this down in a list. I'd be like, oh yeah, I think up, down, yes, no, sound pretty good. Like that's what I would like in my machine. Okay, great. Then you should effectively be able to like not go out and collect the data. Forget that. That's archaic. That's like I hate to say this, but that's like effectively going to the library and trying to find the individual books instead of like having a machine like Google where you can search and actually it knows how to go and find all that data, right? So now there's a lot of speech and a lot of video and audio content out there just from movies and all these things that we do on a daily basis in different languages. That exists as an ecosystem. You don't have to go and manually sort of cherry pick and pick up the data. So imagine if you could just search for data like that, like in a YouTube video, for example, maybe you're searching for, is there the word up, down, and then you go identify those keywords. As you can see here in this example, it's a little small, but you can see, for example, if I give you these list of words that I want, it finds the word up is actually inside this sentence. And similarly, if you look at the next sentence, yes actually exists here. Down is in here, in this sentence. Up is in here. The point is, there's a lot of spoken speech out there in the world. It's a question of how we engineer the system so that we can actually extract information instead of trying to build everything from scratch. So once we have that, then we can do automatic extraction. Automatic extraction is basically taking that audio signal that's there and chopping up at the right bits. So for example, we might say, up is right here. So I'm going to chop that out. And then I'm going to do this across all these different sentences. So these sentences are exactly the same ones that I just went through here. And all of them has some audio signal, which correspond to unique words. And that's what I'm saying. So as you can see, these are the keywords that I care about. That's yes, then there's up, then there's down, there's no, and so forth. In effect, what I'm telling you is that we don't have, in order to be able to democratize this kind of technology, we don't have to go and reinvent the wheel. And every organization, company, you and me don't have to go build the data sets. If we're intelligent about it, given the media that's there, we can go and search for these words intelligently and then build this massive large corpus. And this is something we have actually done. And once you have this data, remember, once you have the data, then you can go into training a model. And then you would effectively be able to say, like, so imagine going back to the email example, you type these words, you can say like, okay, Vijay, I want these words. You just give me that, and out comes this machine learning model without you knowing any of this intermediate goo, right? You don't need to know any of those details. Out comes a neural network model that actually is able to respond to you in your favorite language, right? And so that's sort of the vision that me and many other people are actually trying to unlock in order to be able to support what we call as low resource languages, places where you don't have a lot of technology and a lot of resources to go and build these massive data sets. So I'm not going to get into the technical details, but the point is this: we train what we call as an embedding model. An embedding model is basically a machine learning model, which is architected a very particular way. And what we do is we train this generic model. Beautiful thing about this is you train this black box on something like English, for instance. You train it in English, but you train it in a rather intelligent way. All right, now you've got this black box. Then what you do is then you take it to a new language, for example, like in Telugu, and you say, in my mother tongue, for an example, you say namaste. Well, you give it 5 examples of namaste, which corresponds to hello, right? And then you will update this embedding representation, as we call it, and from 5 examples, instead of having a large corpus of thousands of examples, you just give it 5 words, and out of 5 words, it'll start predicting and responding to you, which is like saying, okay, Google, and the machine waking up. So if I said namaste, the machine would wake up. So it's an incredible piece of technology. And basically what we as a scientific community are all working on is really taking like different languages where we have high resources, which we call as high resource languages. In other words, we actually have a lot of data in these languages. And we train these really good models that get us about like 95% accuracy. And then the beautiful thing about this is that you take that embedding model and then you give it new languages that it's never seen before. It's pretty amazing. It's like asking you to learn something so deep inside the language structures that if I come up to you and I say something in a different language, you'd be like, from the sounds of it, it sounds like, that's the word you mean in that particular language. That would be incredible. It's like a language you've never seen before, but it's like your brain just figures that out on the fly. And that's quite literally, as crazy as that sounds, that's exactly what many of us are all working on. And what I'm trying to show you is that for 13 different languages that it's actually never, ever been seen, there's no data for it and nothing. It's like, it just looks at it. It's got about 95% accuracy, which is mind blowing, right? And so we're not there yet in terms of 1,000 words per 1,000 languages. No one in the community is really there. But it's part of that vision and that goal that, hey, how can we come up with some sort of embedding models and things like that that allow us to kind of achieve that goal, because we cannot rely on those costly pipelines. Now, state of the art is we got all this stuff working on a phone, for instance, which is awesome, right? A phone, you can give it any language, you can say it in any language and it will know what you're talking about. But in reality, what we want to do moving ahead is really kind of putting these things into small little embedded microcontrollers, small little devices. Again, I'm trying to tie this back to the point that imagine if this sort of a technology was actually globally accessible in a wide range of different devices, not just the big consumer electronic devices, right? So how do we enable this? Because it's a really, really resource constrained thing. Right? You've got very little amount of memory, you've got very little power, like dinky little coin cell battery, and it's got to operate for years to, months to years. And if you can enable that piece of technology, then you can really enable access across a wide range of different tasks, across different kinds of languages. And I spoke about just speech, but the same fundamental concept can also be applicable in vision. And so one of the key questions is, how do we widen access to applied machine learning? At this point, I'm going to pivot a little bit. So I'm going to wrap up the first part. I'm just going to have only another 5 slides or so. What we've talked about is that, wow, we take very advanced AI technologies for granted, especially in conversation, we take it for granted. When in reality, the world is a very heterogeneous and rich place, but the technologies don't quite widely, when it comes to speech, which is very personal to people like you and me being able to interact, it's actually a really small sliver of the entire planet that actually is benefiting from it. Now, why am I passionate about this problem? It's because I strongly believe that we've got to widen access to applied machine learning at a planetary scale, not just kind of enabling the niche certain communities. And that requires us to really innovate. We have to understand what the fundamental problems are and how the industry is actually doing things. And we have to build new technologies. And I gave you a very short preview of like, a rather complex pipeline where you can just type something and out comes a model that knows, languages it's actually never seen before. But how can we do more? That's the technology piece, right? That's really being at the forefront at like the elite institutions. But how do we kind of like take a step back and think about widening access to this technology at a planetary scale? Now, if you kind of look at what's happening in the ecosystem, if you look at the kinds of devices that we have, right? I'm talking about servers here, big compute servers that are available for like, big tech firms. Mobile devices, there are, billions of them around the world. And Yeah, we think they're globally accessible. In reality, if you actually look at the serious stats, they're not really accessible because they're really high premium devices at the end of the day that are capable of running all these things. But if you look at these small little microcontroller kind of devices like the one I showed you, there are over 250 billion of them today, and if you project this out, the cost is diminishing remarkably fast. And so there's a lot of potential. If you can enable that intelligence on that tiny little device, you can really unlock the future, right? And speech is just one example of that. But the reality is, when you talk about it from a widening access perspective, you got to empower people. You got to educate people. It cannot be just the ivory towers that have access to this sort of technology, right? And the big tech firms and the ivory towers really, a lot of technology is kind of caught up in very small number of places. And so if you kind of look at specifically in the US and so forth, we are at the forefront of this. And the bigger question I am passionate about answering is, how do we get this out in the hands of many people? And if you look at all the pedagogical courses that are out there, you're talking about very general machine learning at large. There are lots of courses that correspond to things that can run in big cloud servers. However, when you look at it from an accessibility standpoint, what I really care about is this. From an accessibility standpoint, it's these embedded small little microcontrollers that have this remarkable, they're everywhere, they're dirt cheap, But if you look at it from a pedagogical standpoint, what we call as tiny ML, there's very, very little material out there. And so how do we sort of widen access? We want to do something in here. So this is something we have actually done at Harvard as a big initiative to try and get more people to understand this technology because it's cheap and it's accessible. And so we started this sort of effort to actually educate things. And this means, like, we built some of the most pioneering classes in the space, not just residentially. We actually put this on edX, and there's it's only been about 4 months, and it's around 35,000 people are actually taking this course right now. And it's from all the different places across the planet, which is awesome, because now we're able to move the needle forward. We're not only just staying at the very best in terms of what we actually do in terms of research, but even in education, we're moving the needle forward, not just for our residential students, but we're effectively a beacon in terms of indicating about where things are going in the field. And we're doing this in a way where we're actually enabling equity in the ecosystem, not equality, just equity, and bringing up everybody, because TinyML is something that's globally accessible. And we built out 3 interesting courses that have actually been deployed, and there's a 4th one coming around, which takes people from understanding the basics of machine learning, sort of what's actually the technology behind it, what are some interesting applications you can enable. We talked about keyword spotting today a lot, but there are so many other applications you can enable on tiny little devices, and they actually got around to deploying things in their own hands. So for example, we built this little kit that's got a small little microcontroller inside that's $50, which is still really costly, but it's also really cheap if you compare it to most of the things. And this thing has been shipped globally to students of all different places so that they don't need big computers and so forth, but they can still be deploying. They can deploy everything I've talked about today. They deploy it on this small dinky little device, and that's a camera, and that small little device actually responds to keywords in their own native languages. And when I watch those videos, it's pretty amazing. We have done this 1,000 times over, but it's really inspirational when you actually watch people getting machines to respond in their own words, and they decide what words and what not. So I feel like there's something really quite unique that we're able to do in the space because of this technology that we've actually built out. We worked with Google, we worked obviously with all the staff at Harvard, and also Arduino to actually create a global distribution for this kit, which is now, so people can just buy this directly and actually do things without having to necessarily go through Harvard every single time. And we're using this technology in order to move the needle forward, not just for speech technologies, but also in other cases. For example, conservation, wildlife conservation. When you're trying to do wildlife conservation, you don't want to necessarily send people out into the field where they have to put all these small little devices in order to see, for example, if there are poachers who are going after these animals. You want to, if you can deploy these small, cheap little devices in a lot of the developing countries, then they're going to be very accessible to everybody. And then you can put them in, and you can forget about them for about 6 months to a year, because they're so efficient in running all this ML capabilities on board, that then one can actually use this to be able to solve big global scale problems, right? So for climate change or conservation and so forth. And one of the things that we're trying to get students across the planet to actually do is to be able to take part in these things. And we've got a whole system kind of built out to help support this. So I want to wrap my talk up by saying that the future of machine learning is tiny and bright. And it's tiny and bright because if we can get things into the smaller embedded devices, then that's where we can enable 1,000 words in 1,000 languages, being as one example. And the goal really is to kind of shrink things down really small, both in terms of the neural network model size, as well as the time it takes to actually do this. And we want this technology to be globally accessible for people. So a lot of the things that I've actually talked about today, obviously it comes from our lab, but it also comes from like what the community at large is trying to work on and where some of the big problems are. Thank you very much for your time today.
Thank you so much, Vijay. This has been absolutely phenomenal. The future of machine learning is tiny and bright, and it's blowing my mind. So we only have a few minutes for questions. So my apologies that we're not going to be able to get to many of these questions. We'll be able to send out further resources. But to start, I'll share a question from Gilbert Eisner. He's from the Harvard College class of 1953. And Gilbert was hoping you could further explain how you move from the embedding model of well-used languages to those where the data is not as abundant.
Yeah, so this is actually really interesting. It's when you look at the low resource language and the embedding models actually, it's surprising that, wow, an embedding model is able to learn something fundamentally in the structure of the language. But if you look at the linguistic flows, and I'm not a linguistic or speech person, but I build these pipelines that use these things. It turns out the language actually has certain structure, and those structures is really what the embedding model is picking up. And remember, you are fine-tuning it at the end with five examples. So there is that part where it's like you say the word 5 times, and then you tell it whether it got it right or not. But you only have to do that 5 times in order to hit that 95% accuracy, which is very easy because you and I can just kind of stand there and just literally do it. In fact, we probably do this on our devices, like with Alexa and so forth. They'll actually tell you to speak into the device about 5 times. So it's something that's very deployable. Hopefully that answers the question.
Great, thank you. There are a number of questions that are asking in various ways, what about privacy? So how do you and your students talk about privacy in the world of tiny machine learning?
That's a beautiful question. In fact, we actually, when we taught TinyML, one of the things that we embedded deeply into the course was responsible AI, which talks about responsible AI from a design point that you don't think about it after you've done it. You actually start thinking about it when you're designing the models and you're designing your problem statement. And then when you're actually developing your code, how do you actually go about systematically using tools that tell you whether you're developing the model so that it's not biased? For example, in that example of male versus female, we actually teach the students how to actually incorporate tools into the pipeline that model itself will tell you, I'm being biased. So there are techniques that are coming out in that space. And also when you deploy things, you want to have feedback mechanisms in the management of the life cycle. And all of these things are actually taught to the students very much as part of every single process, not as like, oh, hey, by the way, you got to worry about privacy and security and so forth later on. So it's tied into the pedagogical material.
Apologies. And so a similar and related question is about ethics. So in the same way that you're thinking about privacy, how are the ideas around ethics being embedded in classroom conversations?
So for every class, so for example, in the TinyML residential class that I did last year, what we did was we worked with the ethics program that is part of the CS community, where we have philosophers kind of come in and help us understand, not from a technical standpoint, but from sort of like just a thought process itself. So every class now has one class that's dedicated to the topics of ethics. And the beautiful thing about it is that it's done in a way by the ethics team. It's done in a way where they actually work with us to understand the technology and to build a unique ethics class, like a class lecture. So it ties in very deeply into the technology itself. And then they tie in the ethics part.
Great, thank you. So we only have time for about one more question. I would love to ask, just generally speaking, about how the experience of teaching has been for you in the time of the pandemic. You showed us those amazing little kits that you've been able to ship globally, but how else has the experience been for you and for students?
I think experience personally, residentially, has not been so great because I like to really engage with my students, and engaging here means being able to see. I like to read the body language on the fly. You can't do that on Zoom. It's just, you simply do not know whether people are understanding or not understanding what you want to emphasize, what you don't want to emphasize. So that's candidate that's tough, and that's really tough on the student's perspective. And the best you can do really is encourage them to be more interactive in terms of turning the cameras on and so forth. And some of them do, but you cannot force everybody to do that because there are many other reasons why you can't force them. So that's the classroom experience, which I'm summing up as something that we could do better. The other thing is, like, when you talk about like the, doing things over the pandemic. Yeah, as you can see, I've got a mini studio. If you look on this side, like mini studio where Harvard X basically built a micro studio in my office. And then we did all the recordings here. I have never done anything at this scale before. So it was my sort of eye-opening experience. I just felt like last year there was a lot of stuff going out in the world. And I felt like for the students, they really just need something that gets them excited and passionate about something so they can forget about some of the problems they're witnessing and actually focus their energy on something that's constructive that will make the world a better place in the future. So we ended up working with Google for this. We ended up working with Arduino. So we put in a lot of effort in terms of stretching ourselves well beyond Harvard in order to build something at massive scale. And we went from concept to production, as in time to screen. I think it was like literally about 8 months. And in fact, we're writing a white paper about how we did this. It was a remarkable achievement by the staff, the teaching staff, and then also the video production and all of that. It's an incredible achievement.
So I'll ask one final question of you before we let you go for today. Thank you again so much for your time and your expertise. So my final question to you would be, for the alumni community, is there a way that the alumni community can help support equity in technology? Is there one thing that you would like to leave us with to think about?
Absolutely. Thank you so much for asking that. And this is, I'll be honest, this is one of the reasons I actually wanted to come out and talk to you all. As much as I'm excited about telling you about the latest and greatest piece of technology, the biggest thing that I wanted to share across with you is the reason for picking the topic that we picked today was to kind of help you understand that we got to start thinking about things that are well outside of what you and I think on a daily basis. It's about making this technology globally accessible. So things, for instance, direct call for action would be, helping sponsor data set effort. And I'm not talking about sponsoring my lab or something. I'm saying just think about how do we build data sets for low resource languages? Because if we don't do it, who's going to do it? They're not going to be able to do it. So we need to think about technologies that we can enable. So sponsoring research, or maybe startups or whoever is thinking about these kinds of things. That's one. Number two, there's one thing you can invest in. You've got to start investing in the future generation, specifically around AI and ML. While it seems like it's what the whole world talks about, there are barely any teachers who understand this technology to be able to teach this. We are working with K through 12. We're working with universities at various levels because everybody's strapped. This knowledge is just not as pervasive as we think it is. And it needs to be pervasive because, as I told you, this is a technology that has got to be globally accessible. This is not one that's just caught up in some few countries, because that would be a bad thing for just all of us at a global level. So investing in supporting educational activities, like some of the examples I showed you and so forth. And if some of this resonates with you all, please reach out, because we're all trying to make the world a better place by working on TinyML, for instance.
Professor Janapa Reddi, thank you so much for your time today and for sharing your expertise. We really appreciate it.
Thank you for having me. Thank you, everybody.